Perfect. So we've been talking about heat conduction for the last few lectures. It's been, I think, more than 6 lectures on heat conduction, and most of it has been on one-dimensional heat conduction. Okay, so we've been assuming that we've been assuming that let the temperature gradient be only in one direction, and that causes the heat flux lines or the heat flux vector to go in that one direction only. But that may not be the case. I mean, if we think of a real situation, it may happen that you get a temperature distribution which results in a temperature gradient which has an arbitrary direction which changes at different points in space. So for that reason, we'll have to, our assumption of one-dimensional heat conduction may not be valid in all cases. So in that case, we have to use a more general form. So today I'll be using my writing tablet for discussing two-dimensional heat conduction. We can go to 3D as well, but if we discuss 2D, that's good enough to generalize to 3 dimensions. Okay, the only complication, the only complexity we get here is to do with the mathematics rather than the physical understanding of the situation. Okay, so let me share my writing tablet screen with you. All right, so I hope you can clearly see what I'm writing on the screen. I'll use a black colored pen for most work. Okay, so in case you have any problems, do let me know. Okay, so we've been talking about 1D heat conduction, but today we'll be talking about 2D heat conduction. All right, so let's take a situation. So let's take, for example, you have a hot plate. Okay, so it could be not a plate. Let's take a rectangular rod. Okay, so it's a very long. I mean, you can think of the third dimension as a very long rod in both directions. So what I'm taking is just considering one of the central cross sections of that. So this direction I'll call as the X direction, and this one I'll call the Y direction, and well, this one then becomes the Z direction. So let's say that you have some temperature boundary conditions. So there's this long rectangular, long square cross section rod that you have, or rectangular cross section rod that you have, has some boundary temperatures. On the left hand side, you have a temperature of T1. Again, on the right hand side, you still have a temperature of T1. Even at the bottom, you have a T1. But on the top surface, you have a temperature of T2. Okay, so what you've done is you have maintained the temperature on the left, right, and bottom boundaries. It's T1. It could be, you dip that in melting ice, so you can maintain a constant temperature of 0 degrees centigrade. On the top one, you maintain a different temperature. Could be another fluid that is melting, which melts at a higher temperature than water. So let's say this is 20 degrees centigrade. Okay. In any temperature above T1. Okay, and since this rod that we're considering is very long, so in that case, what we get is the temperature gradients along the Z direction will not be there, because it's an extremely long rod, so you can neglect the temperature gradients along the Z direction. Okay, so it essentially becomes a two-dimensional problem, so we don't have to worry about the Z direction. All right, so we'll be considering this, but before that, let us get a feeling of what sort of temperature distribution we'll have. So we'll have a temperature T1 on the boundaries, as we can see, and then on the top one we have a T2. So if I was to, let's say, this is plot the well, not the temperature, let's say the heat flux, then what you would see is that the heat is, as we know, flows from higher to lower temperature. So it's somehow going to, flow from high to low temperature. So what we'll see is probably some sort of, sorry. There's some problem with using the colors on this. Oops. This pen stops working after some time, so I may have to reset this. Sorry for that. Good. I won't touch it too much. So this is our. Sorry, I think stop sharing the screen. So we have T1 on the 3 boundaries, and then I have T2 on the top boundary. Okay, I hope you can see the screen now. All right. So let's. So what I was saying was that if I was to plot the rate of heat flow, then since it's a vector, so what I might see is that the heat may flow something like this. It flows from the higher temperature to lower temperature. So since T2 in this case is greater than T1, so I might see something like this. It should be symmetric. I haven't drawn that to be very symmetric, but assume it's symmetric. Okay. So this is what I expect. But of course, what I want to do is I want to solve for the temperature distribution in this two-dimensional rod that I have, and I also want to solve for the rate of heat flow or the heat flux Q double prime, which can be obtained from the temperature distribution using the Fourier's law of heat conduction. Okay, so that is what we'll do today. So let's get on to it. Are there any questions on this? So we're working with chapter number 4 today. Okay, it's a new chapter. All right. So in this case, let's write our heat equation. So heat equation, if you remember, was the divergence of K grad T was plus Q dot was equal to, plus Q dot by K was equal to rho Cp partial temperature by partial time. Okay, so this was our heat equation. Now in this case, we are not assuming any Q dot. So let's say Q dot is 0 and it's a steady state situation. So this is also 0. Okay, so assumptions are it's a steady state. It's two-dimensional now. We have no generation. And we can assume that K is homogeneous, like in most cases we have done. Of course, these assumptions may not be true, but let us assume these so that we can proceed. Oh, sorry, yes, K should not be there. Okay, my eraser is not working, so I will just strike it off. Okay, thank you for that. All right, so this is our heat equation. Now, since we assume these things, so what we get after using these assumptions, so what we get is the Laplacian of T is equal to 0. Well, and that is what we got earlier as well, except that we were in 1D, so now we are in 2D. So when we write Laplacian of t in a Cartesian coordinate system in 2D, remember our axes are x and y. So when we write that, it becomes simply the dou 2 temperature by dou 2 x plus dou 2 temperature by dou 2 y is equal to 0. So this is y. So that's the equation we have to solve. So it's a simple Laplacian 2D Laplace's equation. All right. So let's solve this equation. So let's move to the next page. Now, what we do in this case to simplify the things, as you will see later, we define a non-dimensional temperature like we did last time, theta. Okay, now theta is also a function of x and y, and we will solve for theta instead of t. Okay, and I'll tell you why we use this, but let's define theta first. So theta is defined as t minus t1 upon t2 minus t1. So let me draw my domain here. So we had t1, 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 and t2. So what you see is that theta again gets nicely normalized between 0 and 1 on the boundaries. On the boundaries it becomes either 0 or 1, and on the inside, since you know that we have boundary conditions of T1 and T2, so temperature inside should either should be between T1 and T2. There's no generation, so temperature on the inside of the domain cannot go above T2 or below T1. Okay, so what we see is that on the boundaries now what we have is theta is equal to 0 on the 3 boundaries, and theta is equal to 1 on the top boundary, and on the inside we have theta varying between 0 and 1. Okay, so that we'll have to deal with nice values when we do the algebra. So that's the reason we do it. Okay, so only for convenience, nothing else. But when we substitute this, the equation remains the same. You can do that. You can substitute t is equal to theta times t2 minus t1 plus t1. So when you substitute in a Laplace equation, so what we get is the same equation for theta. So what we'll do is we'll solve this equation with the boundary conditions which are given on the right hand side. Is that clear? All right, so this is a very nice equation. I mean, I've taken a very nice case for you where we can actually derive an analytical solution for this equation. Okay. So analytical solution is available for this case. So the problem has been chosen in such a way so that the analytical solution is available. Now, in most cases, the real engineering problems you deal with, of course, the heat conduction equation still remains the same. Okay, the equation is not changing. So what changes is the domain shape. You may or may not have a rectangular domain, or what also changes is the boundary conditions. We may not have these elegant boundary conditions as I have given you. Dirichlet boundary conditions on all 4 boundaries. Okay. So with a change in domain shape, which could be arbitrary, it could be an arbitrary shaped domain, a rod which is not completely rectangular. Sometimes it's rectangular, sometimes it's bent, and all these things. Or you have instead of giving constant temperature boundary condition, you give a Robin boundary condition where the rod is heated or cooled because of a fluid which is convecting heat into or out of the system from the boundaries. Okay, so in that case, the equation, the solution, analytical solution is not available. So for that situation, for those situations, we have to use numerical or computational techniques to solve this equation. You may have heard of computational fluid dynamics. Okay, so CFD is a general term which is used for solving partial differential equations computationally. Although we call it computational fluid dynamics because the field started with solving the Navier-Stokes equation, which are the fluid flow equations. But nevertheless, this field is nowadays it means solving general partial differential equations. Okay, so we'll discuss that in the next class when I'll show you actually using MATLAB for solving these equations computationally and plotting stuff. But for today, I've taken a situation where you appreciate the analytical solution for a given situation. Okay, so we'll be using mathematical analytical techniques. Now, these, although it may, the solutions, the real problems may not have solutions like this, but you can, as a first approximation, you can always assume that the rod to be rectangular, because you have to start with something. You can start with a rectangular cross-section rod, assuming that your arbitrary shaped rod is a rectangular rod with the same cross-sectional area, and then you can get a solution. So that will give you some sort of benchmark, and then you can, given more time, you can improve the accuracy by using more and more accurate techniques. But to start with, if you have only a 1 minute or half a minute to solve the problem to get something useful out of it, then you can use approximate the problem with a problem which has an analytical solution available for it. So you should know for what kind of situations analytical solutions are available easily. The other use is that when you write your own codes, we mechanical engineers or civil engineers, we end up writing a lot of, we end up doing a lot of programming or using numerical analysis to solve the differential equations that we have to solve for our work. Okay, so when writing our own programs or computer codes, we have to test them. And how do we test code? Well, what we do is, although the code will solve a general problem, but at least we can solve a particular problem which has an analytical solution available for it, so that we can actually compare the exact value of the error. And then we can develop better techniques, better numerical techniques, and then see how the error goes down, or how one technique is better than the other by comparing the actual value of the error for the two different techniques. Okay, so analytical solutions are quite useful. Don't discard them saying that it's a very theoretical thing. Okay, so let's get onto it. Now, just a quick question. How many of you have heard about the method of separation of variables? So nobody's replying, so I assume that nobody has heard about the method of separation of variables.
Yes, sir, I have. We have
in differential equations.
Oh, you have? Good. Was it in mathematics course?
Yes, sir.
Electrodynamics course.
Mathematics.
Sir,
Mathematics and
the
electrodynamics.
analysis of Laplacian we have studied in the electrodynamics.
Okay,
like,
good.
We separate variables, and finally we have some finite series components.
Very good, very good. So good. For a few, it could be simply a revision, but I will definitely solve it because it's extremely important for heat transfer analysts to understand how to use how to solve 2D heat conduction problems. Okay? It's expected. So let's do that. It's a part of general heat transfer course. So if it's a revision for you, then good enough, no problem. So we are solving this equation, which is our Laplace's equation with the boundary conditions theta equal to 0 on 3 boundaries and theta equal to 1 on the top boundary. So what this method of separation of variables means is that you assume a solution of a particular kind. You assume that your theta, which is a function of x and y, can be separated into two functions, which is capital X function of x and small x is a function of capital Y is a function of y. So capital X and capital Y are just functions, and small x and small y are independent variables. This may not be true. I mean, you cannot always write a function of x and y as a product of two functions separately of x and y, but this is our assumption. If the assumption is wrong, we will reach a point where we contradict ourselves. But if the assumption is right, then we'll end up getting a solution. Okay, so this is an assumption, and I can tell you this works. So the person who solved this for the first time may have assumed this, but then we realize that it works. Okay, so we'll make this assumption, and when we do that, we substitute that into our equation. So let's call this 1. Okay, that's our main equation. So when I substitute that, then I had dou 2 theta. So theta is nothing but x times y by dou x squared plus dou 2 again x times y by dou y squared equals 0. Now you can see that since x and y are pure functions of x and y respectively, then the partial differential becomes a ordinary differential. So the first one, we get y out, and then we get simply a d2 x by d small x squared. Similarly, for the second one, we get the x out. Okay, so I can move around the terms, and then what I get is I get d2x by dx squared. And then I have minus 1 by capital X, and this is equal to, I have 1 by capital Y d2 capital Y by dy squared. Okay, so this is the equation we get. Now remember that capital X and capital Y are pure functions of small x and small y respectively. So that means if you have a function, purely a function of x on the left hand side, and you have purely a function of y on the right hand side, and they're equal, then the only way these two can be equal if this is equal to some constant. Okay, so if this was not a constant, if it was a function of x and y, then they could not be equal, because one side is purely a function of small x, one side is purely a function of small y. But remember, small x and small y are independent variables. They can change in that square domain independently. So that means the only way these can be equal is this is equal to a constant. All right. So so what we'll do now is we will put this equal to constant and solve this equation. Now this constant that we have here can be either a positive constant. So this c can be either negative, can be 0, or it can be positive. All right. So what we will see is, I mean, to show that it is, let's say, positive. So what we do is, I mean, we take 3 conditions now, 3 cases. Okay, so the first case is your c is equal to minus some positive value. So we call it minus lambda squared. Second is c is equal to 0. And third is c is equal to positive value. Okay, so we have to try all the cases and see which one works for our case. Okay, we will see what you see is that you get a contradiction in 2 of these. Again, in the interest of time, I will not show you for each and every case. You can do it yourself. I'll only show you that it works for the successful case, which is this one. Again, you please try by yourself by putting c equals minus lambda square, and you will see that you will at some point when you start putting the boundary conditions, you will reach a contradiction. Okay, so since I already know that C equals a positive lambda square works, I will use that. But we can check that 1 and 2 do not work out. Okay, so we will use 3. So what that means is we will write so lambda is some constant, we don't know what the value is, but at least I know that this constant on the right hand side is positive. Okay, so using this, I can now create two ordinary differential equations, and that was the whole idea. Okay, so what we have done is we have created two ODEs from the PDE that we started with. It's fine. So we have two ODEs, and well, we are experts in solving ODEs, so our life is started to become easier now. Okay, so well, again, you may recall that to solve these kind of homogeneous linear second order ODEs, what we do is we assume a solution of the type. So let's solve the first one, which is d2x by d small x squared plus lambda square x equal to 0. So here we assume that capital X, which is a function of small x, is of the type e to the power of px. Okay, so when I substitute this in the equation, what I get is p square times e to the power of px plus lambda square e to the power of px equals 0. So we have this characteristic equation, p square plus lambda square equal to 0. So what we get is p is equal to plus minus I lambda. Okay, so when you substitute that back, so what you get is your x is since you have two solutions, you get a linear combination of this because it's a linear equation. The most general solution is some c1 times e to the power of I lambda x plus c2 times e to the power of minus I lambda x. Okay, I is your square root of minus 1. Okay, so that's a solution you have, and you may remember that if I expand this using the Euler's formula, e to the power of I theta is cos theta plus I sin theta. Remember, we are working in a real domain here, so the solution we use is, so this is the same as using, well, the constants may not be the same, but let's instead write this as C1, and well, let's see what the book uses. Let's use the same so that we don't confuse ourselves. C1 cos lambda x plus C2 sin lambda x. Okay. So the whole idea is that it's an oscillating solution. It's a harmonic solution, and cos lambda x and sin lambda x are the two solutions. So the most general solution is a linear combination of the two. So that's my x. Is that clear? All right. So I'll also have a second solution, which is for y. Okay, so in this equation, again, I use the same idea, and I will not do it for you. But what you'll see is that your y, which is some function of small y, is going to be some constant. I'll call it C3 because I've used C1 and C2 already, times e to the power of lambda y. Let's use a minus lambda y just to stay the same as the book. And then we have C4 e to the power of lambda y. Okay. Because in this case, your characteristic equation was p square equals lambda square. So you have plus minus lambda, the real values. Okay, so what you'll see is your theta, which is what you were solving for, which was a product of x and y, becomes C1 cos lambda x plus C2 sin lambda x times C3 e to the power of minus lambda y plus C4 e to the power of lambda y. So this is your general form for theta. Okay, now that we have this solution for theta, and I already know that the case 3 that I have given you works. Going back, so this case 3 is what works. So I know that the boundary conditions when I substitute will work for me. I don't have, I think I am out of time now. I'll stop here. We'll have to continue tomorrow. So we'll continue from here. I'll put the boundary conditions for the 4 boundaries, and then I'll finally find the solution for temperature as a function of x and y. All right. So we'll stop here. It's a common room. I have to leave this in time. Any questions before I leave? So I'll stop the recording now. In case you have any questions, please feel free to ask.